Recording.
Yeah.
Yeah, good. It's on. Everything's on record from now. Here, take it away.
Okay, great. So welcome to our third seminar. If you've been to them before, you pretty much know what's going on, but we're just going to explain a few things for those who might be new to it. The talk will be 50 minutes with 10 minutes for questions, and then we will turn the recording off and we'll just have a chat off the record. So feel free to ask any questions you might have then, or questions can also be asked during the talk if you comment on the chat in the Meet or on the chat in YouTube, which we'll be checking as well. But please make sure you mute yourself during the talk. That's really important so we can actually hear Sarah and hear what she has to say. I think that's all the admin stuff. Java, do you want to introduce the speaker?
Oh, yes. Thank you, Kira. So we're very pleased to have Sarah Dean at our seminar series. Sarah is a PhD candidate in the Department of Electrical Engineering and Computer Science at UC Berkeley. She's advised by Ben Recht. She received her BSc in Electrical Engineering and Mathematics from UPenn, had some very excellent supervisors there, like Daniel Lee and Daniel Kodicek. And she's interested in data-driven optimization, design of it, understanding of it, and published a bunch of good works on optimal control, machine learning, computational imaging, and today she's going to talk about the sample complexity of the linear quadratic regulator. Take it away, Sarah.
All right, thank you. Yeah, so I'm Sarah, and like it was said, I'm presenting some work on this sample complexity of the linear quadratic regulator, which I'll explain in more detail what exactly that means and why that belongs in an RL seminar. But this is joint work with a lot of great people. We were all at UC Berkeley when we did this, Horia, Nikolai, Ben, and Stephen. But since then, Nikolai has moved to UPenn and Stephen has gone off to Google Brain. And so this is really like a joint work. It was a long effort, I think started in 2017, published finally last year. So with that, I'll get started. Oh, and I'll also say, like, I think I limited myself in terms of my number of slides correctly, so I should have plenty of time for questions and feedback. So I definitely encourage that. So, right, like I said, the motivation for this work is really that a lot of classic RL works, RL theoretical analyses and algorithm development has sort of been focused on this discrete problem setting with the discrete state space, discrete action space, really inspired by kind of gameplay. And we've seen a lot of really cool successes in reinforcement learning on games, precisely. And that has inspired this interest in applying methods maybe more broadly to bigger real world problems. And that includes things like self-driving cars or robotics, which are now sort of continuous systems that interact physically. And so we're no longer in this sort of constrained gameplay setting. And that's why we're going to look at this setting of feedback control. So control theory is a field with a fairly long history of studying feedback. And so I have this diagram on the right here, which looks a lot like an RL diagram, but I've changed the different vocabulary. So I'll go through that. So instead of an agent, we're going to have a controller. And instead of acting on an environment, we're acting on a plant, which I think is a holdover from chemical process stuff. It's kind of a weird thing to call it, but the environment is the plant. Out of the plant, we observe a state, which I'll call X, and a cost. So unlike in reinforcement learning, where things are rewards, in control theory, it's all about minimizing cost. Same idea, though. And the controller chooses inputs to the plant, and inputs we'll call U. And so this is sort of, a long field has arisen from like process control, like in chemical plants, for example. But much of it has been developed in this case that you have specified models developed from physical principles, for example. I think one of the clear connections to reinforcement learning is when you look at this optimal control problem, where we're sort of minimizing some expected sum of stage costs subject to the dynamics of the system. And here we have X, the state. Remember, U is the input, and W will be our process noise. That's sort of like the stochastic portion, and that's with which this expectation is taken to. So this should be fairly familiar. kind of motivation setting, but maybe with a few different words. And so in this problem, right, this is sample complexity of the linear quadratic regulator. And so linear quadratic regulator, or LQR as I'll call it, is sort of the simplest optimal control problem. It's sort of a very canonical problem. Here, our dynamics are linear. The cost is quadratic, and the process noise is Gaussian. And the classic LQR problem can either be finite horizon, but here we're going to talk about the infinite horizon problem, which is not discounted, but it is sort of this average cost on the infinite horizon. And the part of the reason that this problem is well studied is because it has a very nice and elegant solution. So on the finite time horizon, you can sort of compute the solution with dynamic programming. And on the infinite horizon, we have this like very simple form of optimal actions, which is just this static feedback in the states. So the control input is just some matrix, which I'll call K. So another notational thing is that I'll talk about policies. I'll use the letter K to describe them. Some matrix K times the current state. So it's very nice. It's static. There's no history that you need to keep track of. And this is optimal for the infinite horizon problem. And so here I have a bunch of different variables floating around. So A and B are the dynamics matrices. P is the solution to the discrete algebraic Riccati equation. If you sort of look at the finite horizon solution to this problem and look at the steady state of it, that kind of pops out this discrete algebraic Riccati equation. And P is also what defines the value function here. So the value function here is quadratic. And that's sort of why we get this nice static feedback, which static feedback, which is time invariant on the infinite horizon problem. Okay, so that's the LQR problem. This is something that is like maybe the first thing you learn in Introduction to Optimal Control. And in this work, we're going to look at the sample complexity of it. And our motivating question is basically how many observations are necessary to control an unknown system. So while LQR is well understood, it's understood in this case that you know the matrices A and B, and so you understand the dynamics of the system. If you don't understand it, what would you do instead? And so the sort of setting for a sample complexity problem is if you sort of you don't know what's inside the system, but you have access to maybe excite the system and observe the outputs. The question is, how many observations do you need? So illustrated here is sort of this example where you take observations from one trajectory. I'll go back to this setting and talk about it a little bit later, but for the more simple results, I'm going to focus on a setting where you actually observe n trajectories and you take the final sample from each of them. So it's still n observations overall, but sort of a slightly different sampling method. And I'll describe why a bit later, but this is our sort of sample complexity setting. So this is our observation. And I'll give you a preview now of what the main result looks like. So recall we want a result about how well we can control the system. So it's not just asking how well do we know the system, but for the purposes of our optimal control problem, how well can we do? And so for that reason, our main result is in terms of this relative error of, so K hat will be our sort of synthesized controller based on estimates, so without knowing the system. And it's a relative error compared to the true optimal solution. And what we get here is sort of this several different terms that highlight different components. Some of them are maybe terms we would expect to see for statistical reasons, and other ones are, specific to this control setting. So first, we sort of have an SNR kind of term. So how big is the process noise compared to the injected excitation? Then we have sort of a classic sample complexity type term of square root dimension over number of samples. This is a high probability bound. So delta here is our probability of failure. And then we have sort of this robustness of K star term, which we'll get into what that exactly means later. But this highlights sort of different components of the problem that determine how many samples you would need to achieve a certain suboptimality on your controller. All right, so
I guess there were some questions, just quick clarification questions from Hangout. So someone was, Minshun was asking, sorry, what is K again?
Yes, K is the policy, exactly. So
Right.
K is the control law that takes states and gives you inputs.
Right.
Takes states and gives you actions.
It's also
yeah, but on that same note, what is k hat and what is the relative error? I guess you're going to be defining these, but
yeah, so it's really like the cost, the relative cost of using k hat instead of k star. So k star here is sort of what I defined on the first LQR slide. This is like our beautiful Riccati equation solution that has some cost associated with it, and then there's some additional cost to not using it, and then we sort of normalize it and that's why it's a relative error. So yeah, and I will show this result again with all the details filled in.
I see. Okay, very nice. Thank you.
Yeah. All right. So I will then just preview what I'm going to talk about next. So sort of the paradigm here is something that we've sometimes called course ID control, which is kind of a very simple, I guess, like model-based method, you might say, which is that in the first step, you sort of collect observations from a system, estimate the part of the system that you don't know. So in this case, A and B, and you also estimate some kind of confidence intervals. In the second stage, you use the estimates and the confidence intervals to synthesize a robust controller. And that's the K hat that I had in the previous slide. And then you sort of use that controller in feedback with the system and evaluate your performance based on how well that does. And so this is sort of how I'll go through the next part, is first talk about this learning part, and then talk about the robust control part. And we'll build up to the result that I just showed. So starting with system identification, we are going to consider sort of very simple setting where the inputs are chosen sort of as Gaussians randomly to excite the system with some covariance sigma u, which is sort of the size of our excitation. And we're going to observe the states. And so I'm writing here, the subscript T is sort of how many steps into a given trajectory, and the superscript L is which trajectory I'm on, right? Because remember, we're in this multiple trajectory setting. And then sort of the first thing you would imagine doing is just estimate these matrices with least squares. So just sort of collect all of our final observations together. We have sort of xt and xt plus 1, and then ut, and based on the equation for dynamics, we expect there to be a linear relationship between those. And so we'll just try to minimize that over our n different trajectories. Of course, you might imagine computing these values using all of the data points you collected, sort of even earlier, and that's something you can basically do. But for this first simpler result, we're going to consider this more simpler setting. And so here's sort of like the first ingredient for our main result, which is just the learning part. So how well does this least squares estimator do on finding A and B? And so in this case, this is actually kind of a classic least squares result because of the way that we've sort of chosen these different trajectories to be independent and chosen our data points to be independent. So we have sort of this sample complexity term, this like dimension. So I think I didn't define this, but n is the state dimension and p is the input dimension. So the A matrix is n by n, the B matrix is n by p. And so actually, if you look at this, right, every observation is a vector of size n, and we're trying to estimate something of size n times n plus p. So, kind of squinting, it looks nice that we have this dependence on n plus p. And then divided by, and actually, this should be an n, I apologize. This t should be an n, right, like it was previously, the number of observations. And then we sort of have two different terms for either A and B. Both of them are kind of an SNR style term, but the B one, the term for the B confidence interval is very clearly just this process noise size over excitation size. So the process noise is what's concealing the dynamics from us, what's sort of random about the system's progression, and the excitation is something that we know we're inputting to the system.
Okay, quick question from Vincent. Is X not random? Is it important how it is chosen?
Yeah, so it is important that it's independent from the previous trajectory. I believe that I think like for the analysis, we take x naught to be 0. I think if it was sort of random, that wouldn't really matter either. You could also imagine sort of like if the system is stable, running it for long enough that it's essentially random again. But yeah, this is sort of the system reset case. Yeah. As long as we're preserving these independence between trajectories, then this argument works. And so, right, so we have this SNR term for estimating the B matrix or our control matrix, but for the sort of A matrix, it looks a little bit different. And so the top, we still have the process noise, but instead of just having our injected noise in the denominator, we actually have sort of this square root minimum eigenvalue of something that's sort of like a Gramian matrix. So these matrices, G sort of describes how the inputs propagate to the state, right? So if we sort of think of our dynamics equation, and I'll actually return to this a bit later in the control side, but we think of our dynamics equation and we sort of unroll that recursion. G is just describing sort of how all those U's, those inputs that we chose, affect the state, while F describes how the process noise affects the state. And so this term on the bottom here kind of describes how large our states are getting. And since we observe the state, observing a large state is actually powerful sort of for estimation purposes, because that state might end up being much larger than the process noise. And so for that reason, this is sort of our signal term and our signal to noise ratio. This is sort of the form of the learning result. It's sort of what you'd expect. And we have this interesting observation about estimating the A matrix with respect to sort of system stability, right? So I guess I'll point out quickly is in analyzing linear systems, the concept of stability is very important. So if powers of the A matrix sort of decay to being very small, that's a stable system. If powers get bigger and bigger, that's an unstable system. And that has to do with the absolute value of the eigenvalues. And so you can see that directly here, right? Like G and F will either these are like continuing to blow up with powers of A, or they're getting smaller and smaller. And so this is actually suggesting that an unstable system is easier to estimate because we end up blowing up the states so much. There's other reasons you might not actually want to let your system go totally unstable for learning, but those aside, this is actually like very good. And I'll point out this is different from some previous work on learning from like these linear time series, which relied on mixing time arguments, where mixing time is sort of, if you wait long enough, your covariates are roughly independent. And the problem is that an unstable system doesn't have that property because you're continually blowing the system up instead of getting a decay. That being said, the reason we could get this sort of nice form of the result out is because we made this assumption about independent trajectories and we're not really using all the data we could be using. But I think it illustrates something nice about learning a system. And I'll explain sort of how we get to this type of result. And how it arises from an analysis of sort of random Gaussian matrices. So if we kind of stack together what we've observed, so X will be the matrix of all the final states. Z is a matrix of sort of the previous input and state. And W is a matrix of the noise at the final time step. Then if we sort of look at column, or I guess rows of these matrices, they're sort of independent Gaussian entries, right? So U, we're choosing to be Gaussian, and sort of tracing through how the inputs affect the state, we also find them to be Gaussian and depending on previous inputs, but not on this final U sub t. So we have independence there. And the process noise we've assumed to be independent and Gaussian. And so because of that structure, it's very nice to use like well-developed bounds on Gaussian matrices. And this pops up in the least squares estimate because if we sort of write out the least squares problem using these matrices, we have a Frobenius norm minimization. And the minimizing argument is sort of this pseudo-inverse term, which if we sort of recall that the x sub n is generated by the dynamics, we have our true dynamics term, and then this is our noise term. And so all of the analyses about the error that we're getting comes from this term. And so I'm just going to point out like the high level things about the term that matter, which is this first part, this pseudo inverse. we need to sort of lower bound the minimum singular value here. Or we could just use this to compute data-dependent bounds, which can be useful in some settings because we observe, we're called Z is just like the states in the input. So we do observe that directly. So that's sort of a lower bound that needs to occur. And then the second term is the interaction of Z with W. We don't observe W, so that needs to be bounded. And here we're trying to upper bound these inner products. And by doing those two things, we can get a bound on the error.
So just, yeah, like on YouTube, there was a quick comment. I guess it's a comment that here you expect to see the dependence on X naught. If X naught was fixed, then in the mean of XT, you would expect to see that. So maybe this answers the previous question.
Yeah, that's a good point. Yes, exactly. So right, we would. I'm assuming that I guess here X naught is either 0 exactly or at least random with 0 mean. If it was fixed to some other X naught, yeah, that would appear, I guess, in this norm. And so I don't think it would change the high level results, but it would have some effect on some of these values, I think. So that's a good point. So sort of walked through that analysis and talked about why I like the result and what kind of qualitative things it shows that are nice. But of course, it's not really what you'd want to do with a system. Having this sort of reset ability might not really be realistic. And besides, even if it is realistic, you're wasting a lot of data because you're wasting a lot of time because you're only recording one data point for a long trajectory. And so what about single trajectory? So there are sort of like historically, I guess, on the order of decade have used sort of like ellipsoidal confidence intervals, by which I mean Frobenius norm confidence intervals on sort of the matrix, the estimated matrices. And this is like a self-normalized martingale techniques. Shaba is here. And so I call out this paper, which looked at online learning for the LQR problem. And these confidence intervals do use just a single trajectory, but they give you sort of Frobenius norm confidence intervals, which is different from the operator norm bounds that I showed. Operator norm bounds are maybe a little bit better motivated for the robust control that I'm about to talk about next. And so you could apply the technique, but you'd expect a little bit of looseness from that. However, more recently, I guess 2 years ago now, we actually do have very similar operator norm bounds for linear time series. And this was a group of people at Berkeley, Max Simschwitz, but also Horia, Stephen, Ben, and Mike Jordan, have this learning without mixing result for time series, which is qualitatively fairly similar to the sort of independent result that I presented, although not quite as nice, partially because it's not quite specialized to this sort of linear system learning A and B. So here we get a sort of combined bound on the operator norm of the stacked matrix, which is just bounding the maximum error in A or B. So it doesn't quite as nicely illustrate the trade-off. Not that I think their techniques would be, you would be able to maybe illustrate the trade-off better using their techniques, but it's a little bit of work, some martingale small ball proofs and stuff. But here the result is very similar. I guess I'll point out this difference. We have a signal to noise term, which depends on some constant Cu, which will be a little different from the type of noise amplification that I was showing previously. And then I'll also say that actually in the paper that I'm presenting now, in this sample complexity paper, we also suggest that if you do use all the data, you can always try to bootstrap confidence intervals. And by that, I mean, we have a generative model for our observations. And so using an A hat and a B hat, you can rerun that generative model forward many different times, compute a new A hat hat, B hat hat, and look at the distribution of errors between A hat and A hat hat, B hat and B hat hat. And that should give you an idea of how good your estimates would be. Proving that that's actually formally a correct way to get error bounds is not something that we've done, and I think it would be fairly challenging, but numerically it seems to work fairly well. So this plot just shows this on the bottom is the number of rollouts, so that's n. How many different trajectories are we looking at? And on the x-axis here, we have the comparison of the true error to the bootstrap error. I think it's kind of small, but that's just saying like what was the actual true error that we wouldn't know in reality versus what was the error we computed with bootstrap, and it's usually correct within a factor of 2. So, you know, probably it is fine to use bootstrap intervals with some like fudge factor. And the other benefit of bootstrap confidence intervals is they tend to be like more problem specific and tighter than some of the worst case statistical bounds, which is why we suggest them. Okay, so this actually is the end of our sort of learning section. So if there's any questions about any of this stuff, it would be a good time to take them.
So I actually have a question. So why are these operator norm bounds actually interesting? Because I was imagining, or I was rather expecting that you were going to show something on the quality of the controller that you output in the end. So maybe
Yes.
like pick up like a bunch of extra factors due to going through these parameter errors. Can you explain like how to go from this to that?
Yeah, so I guess, well, okay, a part of that is part of what I'm going to do in the next part is like how to then do the robust control problem. But I guess the reason like at a high level that operator norm bounds are most useful is because you sort of want to look at the amplification of the errors on how the state will roll out. And that's like best captured by an operator norm because that's exactly what an operator norm measures.
Right. Yeah. But I guess my question is that in your bound, you have this dependence on this lambda min parameter.
Yeah.
And maybe that would be going away if you would directly be analyzing the quality of the controller that you're outputting in the end, like, you know, in the standard least squares problem, right? Where for parameter estimation, you have these sort of problem dependent parameters that go away when you talk about the
Right. Yeah, that's a good question. I mean, so it will appear in the final bound because of the analysis technique, which kind of separates them. Whether or not that that has to exist might be an artifact of the way that we do this. Because I'm going to talk about a robust way to synthesize controllers, it's very sensitive to the error bounds that you sort of plug in, meaning that if there's like some term in the error bounds that don't need to be there, it will still always affect your control synthesis problem because you use the error bound to be robust. That's a good question.
Right.
Yeah, there is another question, maybe related to this. It's from Sharon Vaswani, that there was no add-to regularization or any regularization in estimation. Like, wouldn't that help if we added some regularization with this minimum eigenvalue problem? Or?
Yeah, so I think that in this setting, I don't know if this makes it easier, but yeah, in this setting, because of this sort of Gaussian excitation, it's fairly easy to argue about this minimum eigenvalue, even in the data-dependent case, because of like the constant excitation. There's not necessarily a need to introduce a regularization term, which would then add a bias term that then you'd have to look at. But that is exactly like in this sort of self-normalized martingale setting, that there is a regularization term, and that is like a part of the bound that is important. So yeah, I think it depends a little bit on the problem setting. The self-normalized martingale technique also doesn't maybe rely so much on this like persistent excitation to have a good result. So that's another difference for this. This operator norm setting and this least squares estimator does rely on like basically persistence of excitation would be the system identification lingo for it. But what I mean by that is just like noise in every direction that's being injected.
Yeah, a question from Abraham Vinod. Any future directions for getting formal guarantees in the bootstrapping approach?
I think that, so me personally, that's not something that I know we're actively working on, but I think that would be a very cool direction. Because I think bootstrapping is like very potentially useful and like powerful, especially in this like very parametric setting of linear estimates. I don't think any work has been done on proving theoretical guarantees, but I could be wrong in the past 2 years anyway.
Yeah, I guess bootstrapping is, for the Gaussian noise case, is much nicer than for some other noise, right? So if you have binary noise, then bootstrapping needs kind of corrections, whatnot. But for the Gaussian noise, maybe it just works out of the box.
Right. I think the issue for why, like, you know, existing guarantees don't just directly apply is the like independence issue, where you sort of have dependent covariates when you look over a single trajectory. Yeah, but I think maybe similar reasons to why this, why, like, you know, least squares actually works in this setting maybe means bootstrap works in this setting as well. But yeah, I don't actually know. That's would be a good direction for future work. All right, cool. Then pretty well on time. So then let's move on to now the robust control part, which is what do we had this like for a separate learning result, but our motivation was not just to learn the dynamics, but to understand how learning the dynamics interacted with synthesizing a controller. And so this is not the only way to use estimates and confidence intervals to make a controller, but it is, this robust approach does guarantee worst case performance. And so in sort of a two-step setting where, like, once you synthesize the second controller, you're done forever, you know, ensuring that that controller is good is pretty important. So here we're going to look at this robust control synthesis where we have our same sort of LQR problem as before, but I've added this maximization where, because we don't actually know A and B, we're trying to find the best controller for the worst case A and B in our confidence intervals. This is a non-convex problem, and so I'm going to spend the next few slides motivating this alternate parameterization for the control problem. Instead of focusing on the controller K, we'll focus on something called system response variables. So this is the system level perspective on the problem. I first want to just point out, so in closed loop, where you have controller inputs chosen as linear functions, oh, sorry, this is a mistake. This should be an X, not a W. So, right, so the inputs should be chosen as, you know, some linear history of the past states. Yeah, I got a little bit ahead of myself with that expression. And the reason I have this sum over past states is because I'm thinking of very general linear controllers. So while it's true that the LQR problem just has a static controller that depends only on the current state, more generally, you might depend also on past states. Yeah, so past states, this is not, and I'll correct that for the slides online. But if you then look at how those inputs affect the state, you also have this like nice linear rollout where you have a dependence on the inputs and a dependence on the process noise. And so because everything is causal, and by which I mean nothing depends on, like U only depends on X's in the current time and in the past, and X depends on U's and W's in the current time and in the past, you can rearrange this equation, like the linear algebra works out, and you can actually just write the states and inputs as some linear function of the disturbances only. And that's like the system level perspective. This is called sort of the system response of the closed loop system. Because we imagine, right, we have a plant, we have a controller, we have states and inputs in closed loop, but we also have some process noise being injected. And so I don't have to think about the plant and the controller separately. I could just think about the system response, because that's what describes the trajectories of the system. And so that's a system level perspective. And this means that instead of reasoning about K, we can just reason about the interconnection phi with some caveats. So let's see like how we might make that translation. So let's look at our original optimal control problem. I'm not looking at robustness right now. I'm just looking at sort of our standard LQR problem. So I'm minimizing over K. I'm going to make a notational switch now to writing things in terms of signals, which I've been doing a little bit without calling out explicitly, which is going to look like this. So let's go back and forth. Right here, I have sort of like this recursive equation at each time point. These bold-face x's, you can think of them as z transforms of the signal x. You can also just think of them as sort of this infinite dimensional vector of x's stacked together. Z is just like a time delay term, or a time increase term. So it sort of offsets the time indices of this side of the equality from this side, right? This is our same linear dynamics, our same linear control law, and then sort of that infinite horizon average cost I can write as a signal L2 norm. So I've just done a little notational trick to sort of make this expression look a little bit neater. And the reason I've done this is because now I can write those signals x and u as this system response variables times the signal of the process noise. And really just by using this expression and algebraically plugging it in to this one, I actually get now some new optimal control problem that depends only on the system response. And the one thing that I think I want to point out is like I ended up deriving this condition, which is comes directly from the dynamics equation, is that the system response lies in a particular affine space. So it defined by the dynamics matrices. And so not only did I sort of transform the cost, but I also sort of transformed the dynamics into an affine constraint. And so, you know, you can, if you trust me that like the algebraic manipulation just work out, why would you trust me that this is a valid thing to do? Why could I actually solve this equation, this optimization problem for phi instead? And would that be the same as having solved it for k? And luckily, you don't have to trust me that that's true, because this is sort of the system level synthesis framework that was developed by several people at Caltech, John Doyle, Nikolai Matni, John Anderson, and a few others. But this is sort of this framework that just says formally that there is this correspondence. So as long as you are constrained to be in this affine space, then by sort of making a controller out of the system response, this just sort of breaks down how a system response gets formed back into a controller. Then you actually achieve the response you expected. So this is to say that doing this switch, like switching from this optimization problem to this optimization problem, is valid. I'll point out now, and I'll get back to this later, the system response variables are infinite dimensional. So, you know, this looks very beautiful, but actually this is an optimization problem with infinite dimensional decision variables. So, we'll, you know, it's not all free lunch, but it's a very sort of like nice looking problem because we have affine constraints and some kind of quadratic cost essentially. So the reason I bring up system level synthesis to begin with is because of that uncertainty we had in the dynamics. So the key sort of tension is that when dynamics are unknown, you sort of optimize one trajectory that follows unknown dynamics, but then in reality, you actually follow the true dynamics. And it's not really obvious how you would translate one trajectory to another one, at least not in X and U space. For system level synthesis, for system responses, it is actually clear. By lifting it sort of into the system response, which is kind of like lifting from vectors to matrices, we actually have like this exact correspondence. I'm going to go a little bit quick just because I want to make sure I get to everything. But here as well, we have sort of this one-to-one robust correspondence between a feedback controller and a system response, where it's a little bit messy of an equation, but this that I'm sort of highlighting here with my mouse, I think you can see, is the design system response multiplied by this weird inverse thing is the actual response that the system will achieve. And so I'll point out that there's a dependence here on delta A and delta B, which are going to be sort of your errors on like A hat and B hat, which are not things you would know, because if you knew them, you would actually just know the true dynamics, but they are things that you would have bounds on. So this is sort of like our key reason to use system level synthesis, is the ability to translate between what we think is going to happen using our estimated matrices and what's actually going to happen. And so we'll go back to the robust synthesis problem that we had before, right, where we were trying to basically do a min-max, and just rewrite it first in terms of system response variables. So I'm translating it to system response optimal control problem, and then I'm also putting this delta term in. So, right, delta is sort of this system response multiplied by our uncertainty in the dynamics. Notice that we're constraining this response to lie in the estimated dynamic space, and then this delta accounts for the error there. Of course, this problem as written is still not a convex problem because of this term is still a mess. And so for that reason, we upper bound it. And so this is will generally be a conservative approximation, upper bound. of the problem we actually want to solve, but at least it's one that we can sort of reason about, which we didn't know how to do before we were using system level synthesis. And so what I've done here, I'll just look at it again, is I've taken this I minus delta inverse and just done sort of a very crude upper bound of 1 over 1 minus the size of delta. And the size of delta, I'm now just constraining as a constraint in the optimization problem. As written, where I'm minimizing both over gamma, which is the size of that delta block, and the system response phi. This is not convex, but for a fixed gamma, it is convex. And so there, and also, I think with respect to gamma, this problem is unimodal. And so you can sort of use golden section search or something to get a nice solution to this. This convex-ish upper bound on the problem that we wanted to solve. And the other benefit of this formulation is that because it's so easy to track the effect of uncertain dynamics, it's also easy to track the effect on the cost. And so this is sort of where this is our relative error of K term, the cost of K hat. And by that, I mean LQR cost, so infinite horizon LQR cost, compared to the true optimal cost. As long as K hat is synthesized using the system responses from this robust problem, we sort of have this sort of, I think it's a nice expression where we have first, this is the H infinity norm of the closed loop optimal system. That's a measure of robustness of the closed loop optimal system. That's really the important thing to take away from it. Then we sort of have our epsilon A and epsilon B, and notice that epsilon B is multiplied by the size of the optimal controller. So you sort of pay an extra gain on whatever your B errors are based on the optimal controller, because we're always comparing to what would you do if you knew the whole system. And so if the optimal thing to do had very high gains, you kind of pay for it in the suboptimality result. And yeah, then we have a nice constant factor of 5, which is a pretty good constant as far as those go. So I'm ready to revisit our main result now. I guess if there are any questions on the system level synthesis stuff, might be a good time to take them, or I can power through.
There's a question from Nekmi, who is watching us on YouTube. She's asking whether hat K is infinite dimensional or not.
So as I've written things now, that's a good question. Yeah, so hat K, yeah, I guess it's the product of two infinite dimensional things. Essentially, yeah. I guess, yeah, it would be infinite dimensional as written right now.
Yeah,
but I think
the question is, how do you implement this thing?
Yeah, so that will be, I think, after I go through the main result, that's the next slide. I'll talk to that. Basically, you take a finite dimensional approximation, and either it's just an approximation, or you can actually still prove that it's okay.
Okay.
Yeah. So yeah, let's go through the main result, and then written out in its full glory, and then talk about computation. So there's a few different things to point out. So this is the result I presented in the very beginning, now with all the quantities included. So the sample complexity term is the same, that one we're used to by now. But now I have more details. So the H infinity norm term, regardless of what that means exactly, it's a measure of robustness of the optimal closed loop. So this sort of has to do with what's the true underlying system and what are your objectives. If you have sort of a very ambitious control objective, and your system is sort of unstable in some way, maybe this robustness of the closed loop will be low. And that kind of depends on how the problem is set up. But we see that we'll pay for that, right? If we're not, so this is larger when you're not very robust. Then we have sort of our noise term, our sigma W. And then we have the, I did not define it, but this lambda G is just that lambda min of the controllability gradients from the learning result. And so this is sort of how excitable the system is. So this was, I mentioned the intuition before that the more excitable a system, the easier it is to estimate the A matrix. And so we sort of see that if the system is excitable, we get a benefit in terms of this relative error because of the estimation, even though sort of if the closed loop isn't robust, which could happen for unstable systems, then it's not so good. So there's like a trade-off here. And then lastly, I pointed this out before, but the optimal controller gain sort of interacts with the size of the excitation. And so, yeah, the classic example is like, what does this say about like estimating a rock versus estimating like a fighter jet? So a rock is very stable, it's hard to excite. And so even though like maybe the optimal, I don't know, controller for a rock would be very robust, maybe have very low controller gains because you don't really need to actuate too much, it's not very excitable. And so that would still result in a larger relative error. On the other hand, a fighter jet, very excitable, probably learn very quickly by inputting Gaussian noise to the controls, how the plane, the dynamics. So that's good for learning. But then if the closed loop, isn't very robust, or if the gain of the optimal controller is kind of high because you have to actuate a lot, it's still going to be hard to synthesize a good estimated controller. So that's sort of the trade-off that we can look at. So now I will answer this question about actually implementing the controllers. So the system response variables. Oh, yes.
I do have a quick question about the previous slide. So it is the result is stated as sample complexity result. It says that like if the number of samples is big enough compared to something, but that something is full of unknown quantities. So now, like, how are we going to go about this, right? Like, imagine that you actually want to do this. Like, you don't know this.
Right.
So how do you know when to stop sampling? That you have like a reasonable controller when you implement your design.
Right. So the majority, well, okay, that's a good question. Yeah, so this is like, a sample complexity result. It's all about sort of the underlying system and how that affects your suboptimality, which does not make it super useful for actually doing this in practice. There's two pieces, right? The learning piece and then the suboptimality piece. The learning piece, there are data-dependent bounds. And I kind of alluded to them previously, but using those bounds, you don't need to rely on assumptions about the true system.
Okay.
And then the suboptimality piece, sort of an intermediate step in this sort of suboptimality proof, does give you a bound on the performance you expect to see on when you roll it out in your system in sort of basically a data-dependent way. So if you put that together with the errors, you can bound your performance. Bounding the suboptimality, of course, depends on knowing what you expect the performance could be. And so that will always depend on the underlying system. But you can always sort of guarantee that your performance is bounded. So your cost is bounded.
Mm-hmm.
Yeah.
Oh, okay. It's not the error relative to the optimal controller, but it is the total error.
Like cost itself. Yeah, exactly. So you can read it in terms of the cost.
Right. So there was a question on YouTube as well. It's a clarification question about, you probably said this, but how is this H infinity norm defined?
So the H infinity norm, so we have these linear operators, right, which are kind of like matrices. If they were matrices, H infinity norm is the L2 operator norm. While so I have it here, the H2 norm is like a Frobenius norm. So that's sort of the analog to make. And it's actually like fairly precise analog because these things are all just Toeplitz matrices. So that's a great question. So basically, if you look at the synthesis problem, it's sort of this Frobenius norm objective with a operator norm constraint. And that's actually a good question because I was about to talk about how you actually compute this. I was going to say it seems like it would be an SDP, except for this issue of infinite dimensional decision variables. And we have two approximations. One is very simple. Instead of thinking about the system response for all time, you just truncate it for some length L, and that's all. You just only optimize over the first L. You end up with n times n plus p times L decision variables. And you kind of maintain the guarantee as long as L scales logarithmically with the inverse suboptimality. So it's good because it's logarithmic, but L still could end up being quite large. So sort of to achieve a given suboptimality, you have to have a certain truncation length. And this can be kind of large. And you end up with a controller then who has like a sort of state space implementation of size L. So it's kind of this bigger, it's not a nice static controller like you would get if it were the optimal controller. But you do get guarantees still. So it's sort of a nice approximation in that sense. On the other hand, you can sort of constrain this system response to come from a static controller. However, it's not really a convex problem when you do that, but you can make approximations and get a problem that is solvable. It's an SDP again, with now n plus p times 2n plus p decision variable. So that, there's no sort of like truncation length L that you have to worry about. And the controller that you get out of it is just a static controller. So that's sort of the benefit of that. On the other hand, no theoretical guarantees. I think I'm running towards my question time. So yeah, mostly I just have this like last numerical experiment to show, which if you've, I don't know, seen Ben give a talk in the past few years, he probably showed this example, which is sort of very stylized example of, 3 servers which are very weakly connected to each other. So they kind of transfer heat to each other, but very, very weakly, and they're slightly, unstable. There's just a little bit too much load on them for them to cool themselves off. But you do have sort of control input to each of these nodes, which means you kind of have a fan on each one. But electricity is very expensive, and so you really don't want to use the fans if you can avoid it. But let's say we didn't actually know the dynamics, and we just tried to learn it with least squares and do this procedure. What happens? So I'll point out like this is stylized because precisely that these are only marginally unstable. If it's really expensive to sort of turn the fan on and you think the system will just sort of dissipate on its own, you want to avoid turning on the fan. And that's why this is sort of set up for failure. And so these experimental results sort of show that. I don't want to go into all of the details, but this big blue one with the huge confidence intervals, the huge percentiles around it, that shows the cost suboptimality of just using the nominal controller. So certainty equivalence. You estimate a system, don't care about the confidence intervals, you just use those estimates directly. And so what this is showing is that for sort of low sampling regime, so less than 80 or so, you have sort of infinite cost, essentially, by which I mean the system goes unstable. On the other hand, all of our robust controllers, so all the other colors are just sort of different variations on a robust controller, they stabilize the system much better, that you get a finite cost. But then it's true that like once you get out to sort of 100 rollouts, which in the scheme of things isn't very many, then actually this nominal performance looks a little bit better, which is suggestive of, the conservatism of robustness. On the left, I just have this frequency of finding a stabilizing controller, which is just to point out that even though the nominal performance on average looks quite good by the time you get to 100, we're still only like 80% stabilizing. So this was just, 100 trials. That's what these confidence intervals are over. And so kind of suggests that even 100 rollouts isn't quite enough to rely on the nominal controller, because 20% of the time, depending on noise or whatever, you're going to maybe end up blowing up the data center. So this is a motivation for the robustness and just a demonstration numerically. Then I'm going to sort of just talk about some of the extensions of work that we've done, or the work that I've done on this topic since this first sample complexity paper. One is moving this sort of 2-step procedure into an adaptive setting, where we're sort of simultaneously exploiting the system with that robust controller, plus some greedy, Gaussian noise. So just kind of mushing the two together and doing that repeatedly. That allows for a adaptive control with sublinear regret, although t to the 2/3, so not the best regret you can get, which kind of shows the conservatism to some extent of the robust synthesis. And then the other extension is sort of learning while satisfying safety constraints. So this is constraints on the states of the input. One of the benefits of the system level synthesis framework that you wouldn't necessarily get from other approaches to robust control is you can actually also constrain the state trajectories fairly in a straightforward manner. And so now we can reason about exciting the system, but also maintaining safety and sort of keeping away from those boundaries. And we can sort of show a similar result there about learning to control a constrained system. Then I just want to finish by sort of saying what is interesting about this problem. In retrospect, I think I get this from Ben, but in retrospect, it's like a pessimistic view that this is actually kind of a boring problem, right? So exploration was actually kind of easy. Like we just put Gaussian noise in, like that was really easy. And then the exploitation actually wasn't easy, which is why I had to teach you all about system level synthesis and robust control. But a more recent result by Horia and Stephen last year actually showed what I hinted at with the numerical experiments, which was that this certainty equivalence, so just using the nominal controller without worrying about robustness, is actually efficient as long as your errors are small enough, as long as your sampling time is long enough, let's say. And so, you know, even though we went through all the robustness, and there's reasons to use robustness in other settings, but at the very heart of it, maybe exploitation is also easy in this problem. So what is interesting from the RL perspective? I'd like to hear people's ideas. I think one thing I'll say before being so pessimistic is that moving away from linearity, things become very difficult. So nonlinear system identification and nonlinear control are much more challenging. Optimal control in this setting is like, really, there's like no guarantees. You can guarantee stability at best. But many of these strategies do use LQR as a building block. So iterative LQR is sort of like a like sequential linearization kind of method, like alternating minimization for like nonlinear dynamics and non-quadratic cost, and model predictive control, which is a receding horizon method of sort of solving finite time LQR problems at every time step for some limited look-ahead trajectory. So even though maybe the problem at its heart doesn't have a lot of interesting characteristics, it could be a building block for problems that are more interesting. And then, yeah, with that, these are my references. And once again, all of my collaborators.
Yay. Thanks. We do have a number of questions and also virtual claps from the audience. So thanks for the talk. I guess if people want to stay around, just hang around a little more. We have time. Eventually, we're gonna go into the off-record mode. But for now, we're gonna just have the questions. So we can do it two ways. There was a question by. I guess that was mostly answered by Nan, like how does the robust control guarantee compare to the certainty equivalence guarantee? So
I could say a little bit about that. Yeah. I guess like at a very high level, let's see, can I go back to this? At a high level are sort of, oops, sorry. At a high level, the robust guarantee sort of, it's order epsilon. So if you have epsilon error in your dynamics, the robust synthesis gives you order epsilon suboptimality. But our cost here is quadratic, right? So if you're sort of off by epsilon, you would prefer to sort of only pay epsilon squared suboptimality. And that's what the certainty equivalent result gets at exactly. And the reason that this difference is sort of inherent is because our suboptimality, when we're doing this SLS robust analysis, is based on looking at trajectories. While the suboptimal, like, which is not sort of inherently as quadratic, while the certainty equivalent result is all about this perturbed Riccati equation analysis, which, you know, I can't really speak to it, but I heard it was very annoying to actually do.
Mm-hmm. Okay. Do you want to give the mic to some people?
Yeah. We had a question in the chat, and the name's in Chinese characters, and I can't pronounce it. So if you were asking a question about convergence guarantee for bisection on gamma, do you want to speak up and ask it?
Oh, yeah, sorry. That's I used the Chinese account for the Google account. So yeah, my name is Kai Ching. So I'm from Illinois. So very nice talk. I was just wondering if you solved that problem. You said you fixed gamma and solved this convex problem. and then you do bisection for this gamma. So if is there a guarantee for this kind of alternating approach?
So I think the only guarantee we have is that it is sort of unimodal in gamma. And so we implement a golden section search. And so in implementing it, you can sort of look at how much the value changes between steps and use that to sort of have a termination criteria. But I don't know of like an a priori analysis of like smoothness for how many iterations you'd have to do. I don't think we have that. I don't know of one.
I see. But the final results here are for those that you assume that you convert exactly to the optimal of that solution.
Yes, although I think it's always going to be sort of like, as long as the error in convergence is of the same order as the suboptimality,
Yeah.
Then it doesn't really change it that much, but yeah.
I see. So I'm just wondering about the computation part of that algorithm. Yeah. All right, thanks.
Yeah, so actually, on a related topic, I'll say that we actually get much better performance when we don't bisect over gamma. So empirical performance, the guarantee is much worse. But if you sort of leave gamma at 0.99, empirically it looks much better, which sort of suggests that because if you look at what's happening here, by bisecting over gamma, we're really trying to optimize the robust cost versus this is just sort of a robust constraint. And so it seems that sort of constraining to ensure stability empirically tends to give us better performance. And that's just really due to conservatism. And I don't think you could really guarantee that in general.
I see, great. Thanks a lot.
Yep.
There's a question. I think Aditya Mahajan, are you online?
Yes. So are there any lower bounds on this setup in terms of what are the minimum number of samples needed to achieve a certain error performance?
Yeah, so not in this work, but for the estimation part of it, sort of estimating from a single trajectory, the Simschwitz et al. Paper, they do show a lower bound on the estimation. And I believe that Max Simschwitz, I think Simschwitz and Foster maybe, looks at a very similar problem. I forget if they also look at the cost suboptimality, but sort of I think looking at this, perhaps looking at the certainty equivalence with the learning result, there are lower bounds, or I could be mistaken and it may just be a learning result lower bound. I'm not 100% sure. I think with the robust problem, you're not really set up for a lower bound, I guess, because you're sort of synthesizing a controller with respect specifically to upper bounds.
Okay, thank you.
I think we might have a question from Ahmed Touati. Are you here? Perhaps. Let me find the question. The question was to do with the relationship between model-based RL. I'm going to quote it now. I would expect to be optimistic with respect to the model estimates, min A, B in the confidence interval, instead of the robust approach. Could you comment on that?
Yeah, so I think like both the optimistic and the robust approach give you ways of talking about the performance of the synthesized controller in terms of the performance of the true optimal controller, one by doing this worst case view and one by doing this best case view. For this like two-step setting that I'm discussing here, the optimistic one, it would be generally difficult to guarantee results just because it's hard, like you'd have to do something extra, you have to make some extra assumption to guarantee stability. But that kind of changes in the online setting where you're constantly recomputing. And so if things become unstable, that would be sort of a large signal that changes your estimates, which would then change your controller. So I think that there's more reason for optimism in the online setting than the offline setting. And I will say also that like using this robust method for an online analysis, that was sort of a T to the 2/3 regret, which is different from the optimistic approach, which is more of a square root t, which is generally better. Although certainty equivalence sort of also now gets a square root t. But that does sort of illustrate what you pay for the conservatism and robustness.
Right. We do have a bunch of other questions. So one question, which is I think quite interesting. I don't know whether you said that, is that you have a rollout length here, and the question is, what is the ideal size for that?
Yeah. So so to some extent, I view the rollout length as a little bit of an artifact of like this method for analysis that we are using. We're trying to like use independence. And so like, I think ideally, like just from a practical standpoint and like, from a niceness standpoint, it seems better if you just take one rollout and then as long as it is. However, if you look at this system identification result, so this slide has a typo on it. This t should be an n, but this t is correct in the lambda min. And so it shows you that the longer the rollout length, like if you have an unstable system, so powers of A get larger, then you get more signal on estimating A for longer rollouts. But of course, like in practice, that means you're waiting longer time to collect each sample. So like you'd have to kind of consider that. On the other hand, if your true system is stable, you're not really getting a benefit from rolling out for longer time. And so for that reason, like that's a pretty good reason not to wait too long. I think, and I don't think I put this anywhere, but I think that we need the rollout to be at least length n, where n is the dimension of the state, if you have a fixed initial condition. I think if you have a random initial condition, it might not matter.
Right. The question comes to mind is that is there maybe a way to adaptively choose the rollout lengths?
Based on just watching, yeah. I mean, so it should be very easy, right? It's like whether a system is blowing up or being stable, it should be very obvious to detect that. Yeah, I don't know, good question.
And then maybe there is some benefit of doing it, right? And like, either you decided, oh, I'm going to reset frequently, or I'm going to not reset frequently because I'm getting so much signal that this is really good.
Right. And so I think one thing that I don't know of an analysis existing is like actually combining sort of this single rollout analysis with the single trajectory analysis. But sort of in principle, you should be able to combine multiple single trajectories using all of the data. And it should show you like when there's a benefit of resetting a lot versus when there's not a benefit of resetting very often.
Okay. Just a quick question about whether there is an extension to the continuous time case, or people are working on that.
Yes, I believe that there are works in the continuous time case. I think there's like at least, as far as I know, there's at least one about learning dynamics. And I think that I've at least heard of people working on sort of a similar LQR problem in continuous time. I think the difference there is like there's some discussion of sampling, because like whether usually you wouldn't imagine having access to data at an infinite time step. So it's more like sampling from a continuous time system, in which case it looks a lot like learning a discrete time system, but with some transform dynamics, as long as your sampling interval is the same. However, the synthesis problem for a continuous time system would look fairly different. But I think high level, it wouldn't look too different. Low level, there would be some details.
All right, I think we should stop here because I'm like, we are going to continue just chatting a little bit more, but just to, like let people ask if they want to go. I think it's better stop. All right. Okay, so thanks again, Babs, and
Thank you.
Really enjoyed the talk. And then we can continue. Because that like from now on, this is not going to be on record. So